Okay, so as I mentioned on Piazza, I'm going to do a double header today. First, I'm going to lecture on maximal independent set, which should take me until 4 o'clock. And then for those who are gluttons for punishment, I will cover the lecture that I assigned as a recorded lecture on Wednesday on shortest paths. We're definitely into the sort of cool algorithms part of the class now. We're kind of done with techniques, and we're applying them in really interesting ways. I think both of these algorithms are really fascinating. So we talked about maximal independent set last time. Right? An independent set is simply a set of vertices with no edge between any two of them. Okay. And of course, any single vertex is an independent set. Maximum is very NP hard. I will not formalize that, but you can take a complexity theory class and learn about why it's really hard. But maximal is easy with a greedy algorithm. You take a vertex, you throw away its neighbors, take another vertex, throw away its neighbors, keep going until you have no vertices left. At this point, you have a maximal independent set. Right? This is what we talked about last time. The only problem with this greedy algorithm is that it is fundamentally sequential. And I'll come back to that at the very end of lecture. There's sort of a formal sense in which it's very sequential. So if we want to work towards parallel algorithms, how are we going to do that? And we got some intuition on Monday thinking about Ethernet, right? If you have n nodes that each transmit with probability 1 over n, then the probability of exactly one transmission is equal to 1 minus 1 over n to the n, which is about 1 over e. So you have a constant chance of having an exactly one node transmit, and this is why Ethernet works. Okay, so we started to talk about how to apply this idea in the maximum in the context of an independent set. We're not going to aim directly for maximal independent set, but can we at least get a whole bunch of nodes that are independent at the same time? And somebody raised on Monday a very natural generalization of this idea, right? Which is for an independent set, maybe you have each node joins this independent set you're trying to create with probability 1 over its degree, right? This is sort of the generalization of 1 over n, right? If you have some degree d, then in a sense you're in contention with d other vertices to join the independent set. And so if you join with probability 1 over d, that kind of suggests that exactly one of you will join the independent set, right? But this relies on an assumption which is not generally true because you're kind of projecting your own degree onto your neighbors, right? If every vertex had degree d, then having every vertex join with probability 1 over d would kind of make sense. Then sort of, right? Let's consider a uniform degree d graph. Okay? If you think about it, a degree d graph you can immediately conclude has an independent set of size about n over d. Why is that? Yeah? Exactly. Right? So the greedy algorithm implies that the independent set is of size greater than, and there's an independent set of size at least n over d. Just because each time you take a vertex, you only throw away d vertices, right? So maybe it's n over d minus 1, or n over d plus 1. Okay, so if in this context, every vertex decides to try to join the independent set with probability 1 over d, right? Then the probability that exactly one of my neighbors joins is also about 1 over e, right? Just like in the Ethernet setting, right? But that's not exactly what I want, right? Because it doesn't talk about what happens to me, right? But I could instead say, let's talk about the probability that I join and no neighbors do. What's that probability? Yeah? Yeah, is about 1 over ED, right? Yes?
For the 1 over E probability, isn't that the probability that none of your neighbors because a lot of it is like 1 minus 1 over x to n, which is probability that none of them is?
No, because the thing to remember is that there's also a factor d because there are d different chances for, right? So this is just like we said in Ethernet, unless I did something wrong, right?
Oh, so there's actually like a time to
Exactly. You multiply this times d. But this is really where we want to look at things, right? The probability that I join and no neighbors do, right? That's a good thing, right? If I join and no neighbors do, it means that there's nothing stopping me from really joining, right? The problem with these randomized approaches is, just like in Ethernet, if two neighbors both try to join, then you have a problem, right? What should we do in that setting? Well, we could take the approach of Ethernet of just have neither of them join, right? If two nodes that are neighbors both try to join, just kick them both out, right? But if I join and none of my neighbors do, then I can really commit my join, right? I can be in the independent set because nobody else is trying to be in the independent set, right? These nodes let's think of them as volunteers for the independent set. Get to join this independent set that I'm forming, right? Because there's no conflict with their joining. Okay? And once they join, I can discard all of their neighbors because I've put something into the independent set that is a neighbor of all of these neighbors, so they cannot be in the independent set. They cannot be in any independent set that contains these vertices. Yes?
Can you explain again why probability of one node joining is unconditionally?
Yes. So again, the probability that a node joins is 1 over d. So the probability that a node does not join is 1 minus 1 over d. And so the probability that none of my d neighbors join, because they're all making this choice independently, is 1 minus 1 over d to the d, and that's my favorite approximation. Yes? Okay. So is the sort of the shape of the algorithm coming into form here, right? That if I can join and have none of my neighbors join, sorry, if I volunteer and none of my neighbors do, then I can join and all of my neighbors can be retired. And so this creates a lot of progress, right? Because the expected number of vertices that join is n over ed, right? So omega of omega of n over d, right? So we already get an independent set of kind of the right size, right? But it's still only a small subset of the graph. So it's not a good measure of progress towards the independent set, right? But the other thing that we can now notice is that if a vertex has any neighbor join the independent set, then it gets kicked out, right? What is the probability that a vertex has a neighbor join the independent set? Well, we just did the analysis of the probability that a vertex gets into the independent set, right, is about 1 over d, right? So I've got d neighbors, so I expect one of my neighbors to join, right? Or to put it more precisely, there's sort of a constant probability that one of my neighbors gets into the independent set and kicks me out. So I'll actually, in this process, just retire half of the vertices, or a constant fraction of the vertices in the graph, which means I've made a lot of progress towards solving the whole graph, right? The problem is that as I do this, what's left is not a degree D graph anymore, right? So I'm not going to try and formalize this argument because I can't, right? I can't make this assumption of degree D everywhere because it's not preserved as I am deleting vertices as their neighbors join the independent set. I need an argument that applies generally, okay? But this board contains all the intuitions for the algorithm that we're going to be developing, which is that we arrange for there to be a sort of a good chance for nodes to join the independent set. Sorry, we arrange for there to be a good chance for a node to volunteer and have none of its neighbors volunteer, which gives us a large number of vertices joining the independent set all at once, which destroys all of their neighbors, and we're going to argue that we destroy a lot of vertices of the graph in each of these rounds. Make sense? All right, so to formalize this, we unfortunately have to add some caveats to this. We're not going to be able to say all of these wonderful things about every vertex, but instead we're going to define good vertices. So now we're going to take a more formal approach. We're going to define good vertices. Okay, and what's a good vertex? Well, we want to make progress, so a good vertex is going to be one that probably disappears. So we're going to try and reverse engineer, looking at a vertex, how can we say that it is likely for that vertex to actually, sorry, let me fill in some details of the algorithm first. Okay. So now as we formalize the algorithm, we're going to mark each vertex with probability, not exactly 1 over d of v, but we are going to mark it with probability 1 over 2 d of v so that things work out nicely later. Okay. And now, if uv has both ends marked, we have a conflict. We don't know which one should go into the independent set. Just unmark both. And finally, we add the remaining vertices to the independent set that we are building, and we delete all their neighbors. Very simple algorithm. Now, this is not going to construct a maximal independent set, but we're going to argue that this makes a lot of progress. Okay? And progress is going to be measured in the sense of deleting a lot of vertices from the graph. Well, not quite, but I'll add more detail later. I claim that if we do this as many times as we like, we're going to end up with an independent set. Right? So as long as this algorithm doesn't run forever, and it won't because we're going to be marking vertices, right? I claim that I end up with a maximal independent set. So can somebody sort of fill in first the claim that it is an independent set? Yeah?
So since we're only like adding things that have to be object, and when we add them, they have to not achieve.
Good. So everything that is, we have this independent set that we're building. Everything adjacent to it has been deleted. So in our next round, we only consider vertices that are independent of what we have so far. Okay. And because of this unmarking step, they're also independent of each other. So we never create a non-independent set as we add vertices to the set that we're building. Yes? Also, right, when we finish, any vertex that didn't get added must have gotten deleted at some point, which means that it is adjacent to something that we added. And therefore, the set that we constructed is a maximal independent set. There's nothing else that you can add. Right? So anything added is independent when added. So we finish with an independent set. Anything not added, well, the only reason that you wouldn't add it is deleted at some point. So adjacent to something which was added. And so you put those two things together, and this tells you that you end up with a maximal independent set if you iterate this process. Right? So this is actually going to be a Las Vegas algorithm. We know it's correct. The only question is, how long does it take? And the runtime, well, it's equal to the number of rounds times the time per round. Right? How long does it take to run a round? Yes? Yes. This is a parallel algorithms lecture. So I should have asked, how long does it take to run around with a lot of processors? Go ahead.
Yeah, so it'd be common everything, like check everything across the time whether it's going to not.
Yeah, intuitively, yes. If you want to be picky about the computational models, there may be some contention issues and things. Those of you who took advanced algorithms last year, I talked about exclusive read, exclusive write, and concurrent read, concurrent write, and so on and so forth, right? But intuitively, right, certainly, you can have a processor for each vertex that flips a coin in order to decide whether it gets marked. Then for each edge, you can have a processor that looks at both endpoints, and if both endpoints are marked, it can clear both marks, right? And then you can have a processor per vertex that decides which vertices are still marked and labels them as independent set vertices. And then you can have a processor per vertex to decide, then you use a processor per edge to decide if a vertex has any neighbors that have been added to the independent set. And then those vertices, you delete them from the graph. So there's some details in how you manage the data structures and such, but I think it's intuitive that all of this is extremely fast, right? You can basically implement it in constant time in some models and in log n time in some other models with one processor per edge and vertex. So O of log n time M plus n processors. Or O of 1, depending on your exact machine model. But it's certainly, and it's an RNC algorithm. Okay? So the hard part, of course, is number of rounds, and that's what we're going to spend the rest of class analyzing. Oh yeah, sorry, I left out a special case. All degree 0 nodes should join the independent set. Can't flip a coin with probability 1 over 0. So just want to get them in there. In probability land, yes. Okay. Okay, so now for the analysis. Here is where I define good vertices. So we want to talk about progress, which means getting rid of a lot of vertices from the graph. And so a good vertex is one that is likely to vanish. What makes a vertex likely to vanish? Does having a lot of neighbors make it likely to vanish? Yes, in the back?
I propose that a vertex has more neighbors than like the rest of its vertices. Maybe doing like an or something like that.
More neighbors than the rest? What do you mean more neighbors than the rest of its vertices?
If you like sum up the average number of neighbors that each neighbors have, and it's like less than the number of
Okay, so you're worrying about the neighbors' neighbors. Why?
because then like if that means that each of like the neighbors of the vertex in question that has like a lot of neighbors relative to its neighbors. For each like neighbor, the probability that it gets like chosen is pretty high.
Good. So you're on the right track. Right? The thing we have to worry about, like intuitively, you would say a good vertex is one with a lot of neighbors, right? Because you figure, okay, lots of neighbors, one of them will probably get marked, right? But this is not necessarily true, because if each of these neighbors has a tremendous number of neighbors, right, then they all have negligible chances of getting marked, right? So it's not enough to just think about your own degree. You need to think about your neighbor's degree. Okay? And what turns out to work well for the analysis is that a good vertex is one where at least 1/3 of the vertices' neighbors have degree less than the degree of the vertex. Okay? Let's work with this definition. Why is it good? Why is a good vertex good? Well, what is the probability that a good vertex gets marked? Sorry, that a good vertex gets deleted. What does it take for a good vertex to get deleted? You actually need to approach this in steps, right? What is the sort of initial good outcome for getting rid of V? Well, we'd like one of its neighbors to get marked, right? So what is the probability that some neighbor of V gets marked. Yeah? Unpack that. So at least, that's a good thing. We want a lower bound. Okay, so we're going to focus on the vertices that have lower degree, right? Since their degree is lower, their chance of getting marked is higher, right? And just as we did with Ethernet and so on and so forth, we need to phrase it in terms of not getting marked, right? A complementary event, right? So the probability that a particular vertex does not get marked is 1 minus 1 over d of v, right? Sorry, these are the lower degree vertices. Lower degree neighbors. And we know that there are at least d of v over, 1 over 2 d of v, because that's the definition of the algorithm, right? And we know there are at least d of v over 3 of them, right? And this is the probability that none of these get marked. And so the probability that one of them does get marked is 1 minus that. Yes? And this quantity, right, 1 minus 1 over d of v to the d of v is 1 over e, but now we have a 2 and a 3 here, which is 1 minus e to the minus 1/6, which is still a constant. Yes?
What if, like, one of the neighbors gets marked but doesn't actually?
Good. Now we have to worry about the unmarking. Right? Yeah? Yes?
Worry about the fact that some of its neighbors may share neighbors in common.
We have to be careful. Well, it's actually right at this step that we have to worry about this, right? So we've got, maybe the neighbors of V form a clique, right? So they unmark, right? This argument is still correct, right? This argument is just asking for each vertex separately, what is the probability that that some neighbor is marked, right? We're just looking at the neighbors separately. But now we have to worry about the unmarking, right? So let me ask about this. What is the probability that a particular vertex is unmarked conditioned on its being marked? Oh, I'm sorry. I did a bad thing. You don't unmark both. You don't need to. This is actually the clever part of the algorithm. You only unmark the higher degree vertex. So you would think, right? Let me double check that. Yes, you're right. Unmark the lower degree vertex. Okay. So the argument over here was still correct. See, the problem is when I know stuff really well, I forget to look at my notes. And so I'm just going off what I know, which every once in a while has an error. Everything I said here is still valid, right? Because anytime I had two marked vertices, two neighboring marked vertices, I unmarked one of them, so I'm still adding an independent set at every step, right? So all of this correctness argument still applies, right? So what is the probability that a vertex gets unmarked conditioned on its being marked? Given this modification to the algorithm, right? Why do I unmark it? Yeah?
Some higher degree neighbor.
That's right. So this is equal to the probability that a higher degree neighbor gets marked. Right? And now we do have to worry. There's a lot of dependency going around here, right? So we certainly can't argue about independent events happening here. So we're going to have to be careful about what tools we use. But some tools work even with dependence. Yeah?
Good question, actually. Where are the two?
That's in the definition of the algorithm.
Oh.
Okay, this factor of 2 is just, this is here for something that we'll need in about 45 minutes. Okay? Yes?
When we like unmark the lower degree vertex, does like the order we see do the edges matter?
These are all being done at the same time. So indeed, if you could have a whole chain of vertices of decreasing degree, which would result in all but one of them being unmarked. Yes? No, you make an arbitrary choice. Either one is fine. You would probably use some sort of lexicon, like just index of the vertex, mark the vertex with the lower index to break the tie consistently. So, what can I say about the probability a higher degree neighbor is marked? Well, again, we've got this vertex W. If the vertex is higher degree, that means it has a low chance of being marked, right? So what is the probability a particular neighbor of W is marked? Well, it's at most 1 over 2d of W, right? That's for one specific neighbor. But we have a lot of neighbors, right? How do we combine all of these different neighbors? Yeah? Union bound, right? So the probability of a specific neighbor marking is at most 1 over 2d of W. So I lied. I actually needed it here, not in 45 minutes. Okay. There are W neighbors. That's D of W neighbors. That's the definition of degree. Right? So the probability that any of them is marked is less than 1/2 by the union bound. And the wonderful thing about the union bound is that it doesn't care what the dependencies are. Right? The union bound is always true. Okay. So now we can say nice things about good vertices, right? There is a constant factor chance that one of my neighbors gets marked and stays unmarked. Right? So putting these together, the probability that some neighbor of V is marked and stays marked is at least 1 minus e to the minus 6th times 1/2, which is omega of 1, which is all that matters, right? So our definition of good vertex means that every good vertex has a constant chance of disappearing. Right? Because if one of my neighbors is marked and stays marked, I disappear. So that's great. All of the good vertices are going to vanish really quickly. Unfortunately, this doesn't get us all the way because what can we say about the number of good vertices? Can anybody think of a graph that does not have a lot of good vertices? Yes?
Maybe like a star graph.
A star, right? So how many good vertices are in a star? One good vertex. Only the middle vertex is good. So if we just talk about progress by counting good vertices, we're not going to get very far. On the other hand, if you think about the star, it's actually a great scenario for our algorithm, right? Because as soon as that good vertex gets deleted, everything that's left has degree 0, and we finish. Right? So what this says is that we can't really just talk about good vertices, but instead, we're going to talk about good edges. A good edge is one that has a good endpoint. And what I'm going to prove to you is that roughly half the edges are good. And before I do that, does everybody see why this gives us a nice story about our algorithm? Yes? Exactly, right? So goodness, again, does not rely on any notion of constant degree or anything like that, right? Goodness of an edge is just, it has a good neighbor, a good endpoint, and we're going to say that half of the vertices are good in any graph without condition, right? And we've just argued that good vertices tend to disappear, which means that good edges tend to disappear. So we're going to destroy a constant fraction of the edges of the graph in each round of this independent set algorithm, which means that order log n rounds suffice to solve the whole graph. Is that clear? Let me formalize this just a little bit carefully, because we do have to think about, there are some expectations and things in here, right? But we said that the probability that a good vertex vanishes is at least some quantity alpha, which is a constant. Right? That means that the probability that a good edge vanishes is at least alpha. Now, if I tell you that half of the edges are good, that tells me that the expected number of vanishing edges is at least 1/2 times alpha times m, the number of edges that you have, right? Which means that the expected number of surviving edges is at most 1 minus alpha over 2 times m. Right? So the expected number of edges is only a constant fraction of the number of edges that you start with. Yes? So after k rounds, the expected number of surviving edges, right? So here we use something that, again, does not depend on, we have sort of an expectation of an expectation of an expectation, right? So these constants multiply. So when k reaches log base alpha of m or so, we'll expect to have only a constant number of edges. And at that point, we're done, right? We can solve it however we like. Okay. So does everybody see that all I have to do is are there any, like, I can go into more detail about this if you like, but if everybody's satisfied with this, I can just go on to the last thing that I need to show, which is that we expect a constant fraction of the edges to be good. Yeah? So there's a few different ways to look to develop a high probability bound, right? So what I can do here is actually run order log m times until the expected number of edges remaining is half an edge. Okay. So at that point, since there's only a half an edge remaining expectation, that means there's a 50-50 chance there are no edges left. So I'm done, right? So this already gives me an algorithm that succeeds with probability a half, right? Now at this point, I have a few different choices. One is I could say, if it didn't work, start over, right? And then if I do it log n times, it'll succeed with high probability. Here I actually have an easier approach, which is if I run it another order log n times, then the expected number of edges that remains is 1 over m squared. Okay. If the expected number of edges is 1 over m squared, then what is the probability that I'm not done? Well, it's also 1 over m squared, right? Same argument. So if that just says that all I need to do is run until the expected number of edges is 1 over a polynomial, and now I have succeeded with high probability. Okay? I'm getting sloppy because I figure you're getting used to a lot of this stuff. But if any of you want more precision, just raise your hand and ask, and I'm happy to go into more detail because this is what you're supposed to be learning. Okay? All right. So the only remaining claim, that half the edges are good. And this is not dependent on any randomization or anything. It's just a structural result about graphs. So let VB be the bad vertices, the ones that are not good. VG are the good ones. And we want to count edges with both ends in VB. Okay. So what I'm going to do is I'm going to direct every edge from its lower to its higher degree endpoint. And if they're equal, I'll use my tie-breaking rule that I defined before, right? Just the smaller index. Okay. So if I'm directing from lower to higher degree, what does it mean for V to be bad? Yeah? Exactly, right? di of V, this is going to be the in degree, is at most d of V over 3. That's the definite, right? A good vertex is one that has that has many higher degree neighbors, right? Right up there, at least. Well, sorry, that has many low degree neighbors. So a bad vertex is one with most of its neighbors have higher degree, which means that most of its edges are directed outwards, right? And of course, I can write d of V as di of V plus do of V over 3, where this is the out degree. Right? So now if I sum over all the bad vertices, their in degree, that's less than or equal to 1/3 of the sum over all of these bad vertices of in degree plus out degree. Right? Yes, question? Yes. So again, the definition of a good vertex is at least 1/3 of its neighbors have degree smaller than itself. Right? Now, how did we direct the edges? We directed from lower to higher. So a good vertex is one where at least 1/3 of the vertices have degrees smaller than me. So that means that the edges are going to be directed towards me. Right? And bad is the other way around. Okay. All right, so now I multiply both sides by 3, and so I have 3 di of v over here, and I have a di of v over here. So what this tells me is that twice the sum of the bad in degrees is less than or equal to the sum of the bad out degrees. Yes? Or in other words, that the sum of the bad in degrees is only half of the sum of the bad out degrees. So, I don't really, I can go through the math if we need to, but let me see if I can convince you about this intuitively, right? D out of V is looking at all of these edges that are leaving bad vertices, right? There's a certain number of edges leaving a bad vertex, right? The total number of those edges leaving a bad vertex is the sum of the out degrees of the bad vertices, right? Where do those edges go? Where are their other ends? Where do they point to? Well, only half of them can go to bad can go to bad vertices because the bad vertices only have half as much in degree as they have out degree. So this tells me that half of the edges leaving bad vertices have to go to good vertices. And so we're really done. I mean, there can also be vertices with both endpoints good, but that only helps us. So do people buy this, or do you want me to work through it in more math? Like you can sum up various degrees and cancel things out and so forth, but I think this makes clear what's going on. Yeah? Okay, so we're done, right? We have shown that half of the edges are good, and we have shown that good edges have a constant factor chance of disappearing, which gives us all of this and lets us conclude that our algorithm needs log n rounds to have a high probability of destroying all of the edges, at which point everything has degree 0 and gets added to everything remaining has degree 0 and gets added to the independent set in one final step. Any questions? All right. If you do this really carefully, you can show that you only need M processors, and you can do it all in log n time. At least, I mean, you can do all log n rounds in log n time. So this is a pretty close to optimal algorithm, right? You're doing, right, the sequential algorithm is going to take linear time, right? M total work. Here, we're using M processors that run for log n time, so that's M log n work. So it's still pretty good. And there are some weird techniques that you can use to drive it closer to M, but for this class, certainly M log n is good enough. Yes?
Is there any analysis to get closer to the maximum than like the 3D algorithm?
our extremely pessimistic results about the ability to find a maximum independent set make me pessimistic about proving anything about the size of the independent set that you find. All that we know is that it is maximal. Okay? Yes?
That's not like the proof, but more just about like RNC here in the neural.
Yeah, actually, this is what's known as ZNC, if you remember the complexity classes that I defined, because it's Las Vegas.
But I guess I'm just wondering, 'cause I know there's no maximal set question, especially the question with parallel. I guess like just for the log in time for like the round, is it like, I guess I'm trying to like say like it takes like log n or time.
Yeah, I think it's a fair question. You should feel free to assume that sort of obvious basic operations like adding up a bunch of numbers or finding the minimum of a bunch of numbers and so on and so forth can all be done in NC without you having to specify the details of how that is done, right? Again, if you've taken advanced algorithms, you know all this is true. If you haven't, you can just assume that it's true. Okay? So the focus is really just on, like here, it's really about analysis of rounds and probability of things vanishing and so forth. Okay? Yes?
Can you repeat like the final argument about like how, like after you got the last statement on the board, how do you bound these?
So I'm not bounding VB, I'm bounding edges. Right? This has nothing about how many bad vertices there are. We saw, in fact, in the star that almost all the vertices might be bad. This is only bounding bad edges, which are edges that have both endpoints bad. Okay? And the argument there is that in order to have both endpoints bad, you have to, we've directed these edges, you have to leave a bad vertex and also enter a bad vertex. And what we argued from this final result, which is probably better stated, or is more intuitive if I state it this way, is that if you look at all of the edges going out of all the bad vertices, only half of them can possibly be entering the bad vertices. Okay? All right. Let's see. So there's two more things. One thing I'll just mention quickly. One is that we've got this nice randomized, this nice parallel algorithm for maximal independent set. What it's finding is not anything like the greedy maximal independent set algorithm. And in fact, what is called the lexicographically maximal independent set, which is to say that you want the maximal independent set that comes first in the lexicographic ordering. If you order the vertices in some way, you can define a lexicographic ordering on subsets, right? And so if you ask for the lexicographically first maximal independent set, well, that's trivial to find sequentially because that's what the greedy algorithm will find, right? But this is actually one of the p-complete problems. I talked about p-completeness last time. This is a problem that we do not have an NC algorithm for, or an RNC algorithm for. And if you did find an RNC or NC algorithm for this problem, you would have shown that P is contained in NC or RNC. Right? So this is one of the hardest problems to parallelize, and we suspect that it cannot be parallelized because we think that not everything that is polynomial time solvable is solvable in polylogarithmic time in parallel. Okay? So this had to find a different kind of maximal independent set. Okay. All right. What remains to be done is something which is I guess you could say it's its own special subfield of randomized algorithms, but we haven't encountered it yet, so this is our first chance. We've talked before with things like hashing about decreasing the amount of randomness that is used by an algorithm using tricks like pairwise independence. Well, what happens if you manage to decrease the amount of randomness used by the algorithm to none? Well, then you have a deterministic algorithm. And some people are curious about, some people are interested in whether it is possible to solve a problem deterministically instead of with randomization. And so there's this whole interesting sub-area of algorithms called derandomization, which says, can you take a randomized algorithm and turn it deterministic? And this actually is not generally done by taking away all the randomness directly, but instead it is done by creating a sample space for your randomness that is so small that you can try all the sample points. And that gives you a deterministic algorithm, right? If you have some set of sample points and you show that there is a chance of success among those sample points, then of course if you try them all, you will succeed, right? So we are going to, after a break, de-randomize this parallel algorithm and get ourselves a deterministic maximal independent set algorithm. But take your break first.
Hi, so I missed the lecture on theory.
Okay.
I forgot what so I don't know what P complete means.
Oh, well, I mean, you should watch the recording, but P-complete it's like NP-complete, but for parallel algorithms, right? So P-complete means that if this problem can be solved in NC, then all of P can be solved in NC. Yeah. The completeness is a general notion for complexity classes. Okay, everybody's sitting down and waiting with bated breath to find out how to de-randomize this algorithm, so let's get started. De-randomization. The general idea of de-randomization is to use pseudo-randomness to make the sample space so small you can try every point. And the other important idea of de-randomization is don't write a new proof. Right? You already did all of the work of proving this randomized algorithm is correct. You just need to design your randomization so that all of the statements that you made in your proof, which maybe assumed full independence, are still true for whatever kind of distribution you pseudo-randomly generate. So that and this may require tweaking the proof a little bit. We will do so in this case. This proof shows us what we need to prove. We're going to need to prove it slightly differently once we use a pseudo-random generator. Okay? All right. So what kind of pseudo-randomness might make sense here? Well, first of all, we're not going to de-randomize the whole algorithm. We're just going to de-randomize one phase, right? We don't, these phases operate independently of each other, and what's important is that in each phase, we get rid of a lot of edges. So we just need a deterministic algorithm that will get rid of a lot of edges, and then we'll be done. Or we put another way, we need to de-randomize the round that gets rid of, and argue that the number of edges that remain is small. Okay. And since our proof is focused on edges, it's kind of natural to talk about pairwise independence, right? So the key idea is going to be to mark the vertices pairwise independently. That's going to be the only change in our algorithm. Instead of flipping independent coins for each vertex, we'll use a pairwise independent random generator. Okay. Now, we remember that, right, to do a pairwise independent random number generator, we can just set our jth number xj equal to some aj plus b for a and b chosen randomly from our appropriate prime field, right? Now, here, our algorithm wants to mark things with probability 1 over twice the degree of a vertex, right? This is the granularity that we need. Clearly, it won't matter if we're off by a little epsilon from this. That's not going to change anything, right? So my claim is that if we use a prime that's around n squared or something like that, right, then that's going to give us the granularity that we need to mark things with probability 1 over twice the degree. Yes? Yeah? Well, if you look at where we, at the arguments that we made, we sort of did this 1 minus 1 over d to the d type of argument. So if instead it's if instead it's d plus 1 or something like that, that's not going to change anything, right? And that's really the only math that we did. And similarly, like a union bound here, right? We ended up, we summed up and got, you know, we took d of w times 1 over 2d of w. If it's 2d of w plus a little bit, then certainly it's going to be bigger than a third as opposed to a half, and that will still be fine. And that's the only math that we did, really. Okay. So we're going to de-randomize by using a prime p, which is somewhere around n squared. Okay. And we only pick this, we pick this prime once, and it doesn't have to be a random prime, right? So we just have a prime that makes this work. But if we are able to prove that this algorithm works, as we did here, that the expected number of edges removed is a constant fraction, right? Now we're talking about an expectation over random A and B. Correct? So if over a random A and B, the expected number of edges removed is a constant fraction of m, then certainly there is some A and B for which the expected number of edges removed is a constant fraction, right? You can't have everything be below average, right? So the expectation over A and B of edges removed is omega of m. That means that there exists an A and B such that the edges removed is omega of m. So if we want a deterministic algorithm, let's just try all pairs A and B. right? A and B are numbers between 1 and n squared. So we just have a polynomial number of different seeds that need to be tried. Each seed will yield a different set of edges that get removed. One of those sets of edges will be large. How long does it take us to try all of these different seeds? Yeah? Exactly, we're in parallel. So in fact, all of this extra seeds just turns into more processors, right? So now instead of using m processors, we're going to use n to the 4th times m processors, which is maybe not something you want to bring to Google for implementation, but is fine for an algorithms class, right? It's still polynomial number processors. It's still going to be NC. So this is how easy it can be to de-randomize an algorithm, right? You just use pseudo-randomness with a small sample space, and you try all the possibilities. Yes? So this gives you an algorithm for finding a good set of edges to remove in one round, right? So you basically branch out over these n to the 4th possibilities. You check, okay, this is a good set of edges to remove it, and now start the next round all over again. So in the next round, we again have to randomly, we have to simulate the randomness, which means trying all possible A's and B's for the graph that remains. Okay? And we do that again in each round. We exhaust all the A's and B's in each round against the graph that came from the previous round. Okay? And notice we don't have to, it's not like a branching out, right? We don't have to, for every graph from the first round, we don't have to try its second round. We just take one good graph from the first round, and that's the one that we use in the second round. So we're only using n to the 4th times m processors in each round. Okay? Any other questions about that? All right, so all I have to prove is that pairwise independence suffices. Let's look at where we relied on randomness and think about whether pairwise independence is enough. So our analysis is really just these boards, right? So it came down to two things, right? We wanted to talk about the probability that a vertex gets unmarked conditioned on its being marked. And we also wanted to talk about the probability that some neighbor of a good vertex gets marked, right? So let's do the easy case first, okay? Are we okay in our analysis of the probability that a vertex gets unmarked conditioned on its being marked? Yes? Good, good. So both of those statements are important, right? The point is, we are looking at, we're conditioning on W being marked, and we're looking at the neighbors of W, right? So we've got some conditioning going on because we conditioned on W being marked, right? However, because of pairwise independence, we can say that each single neighbor of W has the same probability of getting marked as it had before, right? It's still less than 1 over 2d of W, right? Because we're going for pairwise independence. And so this is why one-wise independence would not suffice, is that we need the independence of each individual neighbor from W. Yes? But once we have the independence of each individual neighbor from W, we can read off the probability that W gets marked. And now, to that, we just applied the union bound, but the union bound doesn't need any independence, right? All of the neighbors of W can be dependent on each other, and will be, but it doesn't matter for the union bound. So this part of the analysis doesn't have to change at all, right? Any questions about that? Okay. What about the other part? probability some neighbor of V gets marked. Yeah?
Well, I think currently it is assuming that more than pairwise dependence, but we can replace it with a union bound.
Well, we have to be a little careful. You are correct that it is assuming more than pairwise independence, right? This is actually assuming full independence because I'm multiplying all of the marking probabilities of the different vertices. Right? Right? I'm taking a full product of all the probabilities, which is assuming full independence. Right? And we don't have that. We only have pairwise independence. So this is where we have to tweak the analysis a little bit. So, probability that we are unmarked, condition on marked. The analysis is fine because it depends on union bound. Right? We have problems with the probability of some neighbor being marked. Right? This assumes full independence right now, which is no good for us. So we need to change this argument. It's still true. Okay. Let's write pi to be the probability that neighbor I is marked. Okay. Actually, let's let xi be the event that I is marked. So pi is just the probability of xi. Okay. Now we know the definition of a good vertex is that the sum of the pi's, right? A good vertex is one where a lot of its neighbors have large pi, right? The sum of these pi's was at least, it had at least a third of its neighbors of lower degree. Each of those got marked with probability 1 over 2 dV. So the sum of the probabilities was at least a sixth. Okay? So the expected number of neighbors that gets marked is a constant. Right? And so what works well with pairwise independence? Well, Markov's inequality still works with pairwise independence, right? If I tell you that the expected number of neighbors that gets marked is a constant, you can use Markov's inequality to upper bound the likelihood that a neighbor gets marked, right? Unfortunately, we want a lower bound, right? We want to say that there is a reasonable likelihood that a neighbor gets marked, as opposed to an upper bound on the probability that a neighbor gets marked, right? So we want a Markov-like lower bound. Something that just worries about the expectations and therefore works with pairwise independence, but that gives us a lower bound instead of an upper bound. Sorry, is there a question? Okay. So the claim is that, let me put this as a lemma. If the xi are pairwise independent, then the probability of the union of the xi, probability that something gets marked, is at least 1/2 of the smaller of 1/2 and the sum of pi's. So there's a bunch of hedging in case the numbers get too big. But basically, this says that sum of pi, as long as it's not too big, sum of pi is also a lower bound on the probability event, right? Markov would use sum of pi as an upper bound. This is saying that as long as you're pairwise independent, it also works as a kind of a lower bound. And that's intuitively nice, right? That you can treat the expectation as kind of a probability in both directions. Okay. Remember that for pairwise, you get a much better bound of 1 minus the product of 1 minus the pi's. So you lose something. But of course, that sum of pi's is the first term if you expand this product, right? Right, this is 1 minus the sum of pi's plus sum of pi pj's and so forth. So it's really saying that this term is dominant. Okay. The proof, if you think about it, the Markov inequality comes from looking at the probability of a union as upper bounded by the sum of the probabilities, which is the start of the inclusion-exclusion theorem, right? So that's what we're going to use. The probability of a union of xi's, well, it's less than the sum of the probabilities of the xi's, but inclusion-exclusion tells us that it is greater than the sum of the probability of the xi's minus the sum of the probability of the xi's and xj's. Yes? And if we're working with pairwise independence, these intersection events still look like independent events, right? Because there's only two of them. So basically, pairwise independence lets us use inclusion-exclusion up to two terms, right? The union bound is using only the first term of inclusion-exclusion and therefore works regardless of independence. Once you have pairwise independence, you can use the second term. If you have three-way independence, you can use the third term. And so you can get tighter and tighter bounds by using more and more terms of inclusion-exclusion. Let's suppose the sum of the pi's is smaller than 1. This is why we have the extra halves, because we want to consider the general case. But if the sum of the pi's is less than or equal to 1, then the probability of the union is greater than the sum of the probabilities of the individual events minus sum over I less than j of probability of xi intersect xj. And this is equal to the sum of the pi's. What's the probability of xi and xj if everything is independent? Yeah? Exactly. Okay. Which is, I'm going to just look at both directions of the summation now. Right here I was taking I less than j. Here I'm basically counting everything twice. And if I just throw in the diagonal terms as well, that just makes things smaller. But the sum over of all pairs of pi times pj, that's just the sum of the square of the pi's, right? Right? But of course, I can rewrite this as, because I have a sum of pi's in both places, sum of pi times 1 minus 1/2 of the sum of pi's. Right? But I assume that the sum of pi's is less than or equal to half, so this is at least half of the sum of PIs. So as long as the sum of probabilities looks like a probability, you can think of it as a probability. Okay? All that remains is the case where sum of PIs is too large, right? So else, if some single PI is greater than a half, well, then we're already done, right? Because if there's a single PI that's at least a half, then, of course, we have at least a half probability of getting that PI. And we don't need to worry about the others. Okay? Otherwise, we've got a sum of PIs greater than 1, but all the individual PIs are less than a half. So start ignoring PIs one at a time until we are left with, right, each time I throw away a PI, I'm throwing away at most a half. And so if I start with something that's bigger than 1, I end up with something that is at least a half, right? So I can keep doing this until I'm left with a sum of PIs that is less than 1, but at least a half. Okay. And the first analysis applies to this subset. So the probability of the union of the xi's is at least a half times a half, or a quarter, and that completes all of the cases. So basically, if the sum of PIs is not really large, then your probability of success is at least half of the sum. If the sum of PIs is really large, then your probability of success is at least a half. Either way, you're done, right? We have shown that just using pairwise independence, we still have a constant probability of marking a neighbor of a good vertex. And that completes the proof that pairwise independence suffices, and therefore that you can de-randomize this algorithm and end up with an NC algorithm for independent set. Without doing anything else clever, right? All the cleverness is in the randomized algorithm. And that's the end of the story for maximal independent set. Any final questions? Yes?
Maybe like on the else, we get one.
I mean, you can probably improve the constant factors, but in this class, we don't care. Anything else? Yes? It is not used a lot in practice because it often costs you a substantial polynomial factor, right? On the other hand, it's very important in complexity theory for showing where randomness is necessary and where it's not. And there have been some incredibly powerful de-randomization results that show that sort of whole classes of problems can be solved deterministically. All right, for whoever still has energy, I will, in 5 minutes, start lecturing on shortest paths, but we have to move to room 155 across the hall, because apparently there's a party in here or something. I mean, it can't possibly be as good as the party that we just had, but